Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief at Integrating Materials and Manufacturing Innovation. I've got a brand new paper to talk about. It's about detecting little pores or defects in cast metal, whether they're cast in sand or in additively manufactured components. This group of authors is going to try and use computer vision to detect these defects. Now, this work comes to us from lead author Laura Arias-Martínez at Alegre in Spain, and corresponding author Francisco Jáñez-Martino at Universidad de León. Now, the authors point out that the metals industry is a bit behind in approaching Industry 4.0, and they have the goal of transforming these traditional foundries into smart foundries. And part of that is going to be having automatic systems to detect defects in castings. And there's lots of defects that can happen, but porosity is one of the most critical ones, right? If you've got a pore in your material, that makes it a lot weaker. We want to find those. But porosity comes from two main sources. One could be gas presence, and the other could be material shrinkage during the solidification process itself. So there's a lot of prior art here to consider. An important one is the actual tool they're going to use. They're going to use an image detection tool known as You Only Look Once, YOLO, to define these things. The specific one they're going to do is YOLO version 3 v3, which has been cited 35,000 times at the time of recording this on arXiv. Very popular foundation image model. But it also builds on other work by other people who've also tried to use computer vision for detecting defects in cast aluminum parts. For example, this work by Fuchs and Kruger and Garbe, where they actually looked at CT scans and used image models to try and find defects in their materials. When it comes to generating data for this model, they actually made materials. On the left, you see a sand mold and the cast part that came from it. And on the right, you see a binder jet system, which is able to binder jet print the mold, and they were able to cast into it. They actually have details on the actual fabrication, which I appreciate, how they made them, what their yield was, what the metals were they used. So you can see that for both the 3D printed mold and the sand casted mold. Ultimately, though, once they had the part, they had to take it out, cross-section it, cut surfaces, polish them according to ASTM E3, and then they were able to analyze those surfaces to collect images for the model. They collected 204 images, which they're going to use to fine-tune YOLO V3. When they collected images, here's some examples of what you see. In the bounding boxes, both in green and in red, you see different types of pores. They point out that the green ones are due to shrinkage, and the red ones are due to gas pores. There are more gas pores, there are fewer shrinkage ones, and the shrinkage ones tend to have more difficult shapes. They're not quite as simple or uniform shapes to be found. When it came time to implement machine learning, I like this. They actually used Google Colab, which is awesome. They've got the notebook there. And their results showed that they were able to detect the two different types of pores very, very quickly. 30 milliseconds versus 56 milliseconds per pore, depending on which type of defect they're looking for. When you compare that with the manual inspection that can take sort of an hour per image, this is a crazy improvement on their time. But is it good? Well, it kind of depends. For the different types of pores, you can analyze the results as a function of your confidence threshold at 25% confidence, 50% confidence, 75%, and your error sort of changes, right? For example, if you're willing to tolerate a lower threshold of confidence, then your recall is actually quite high on pore type 1, right? They get 60% of their pores. If type 2 is going to be lower, it's only 0.377. But still, this sort of suggests that we can actually use this as certainly a starting point to find defects in materials effectively. There were some differences clearly between the two different types of pores, and they point out that it's worth highlighting here that the most pores detected corresponded to the gas pores. There's just more of them, and it also might be due to the irregular shape of the dendritic pores, whereas the gas pores tend to be more round. So take a look at this paper in the latest issue of IMMI.